Hello and welcome to our new webinar on PVC application. Today we will talk about the torque rheometers. Last time I spoke about laboratory mixers. This time I will talk about laboratory extrusion, laboratory extruders, different kind of types of extruders. But later on, especially, we will see the capillary rheology, so the measurement of the flow behavior of a PVC. I've already prepared the machine and we will run our trials in a few moments. But before I go into deep here with the hands on, I will show you some slides to explain what we are going to do. In my last webinar, I did explain more details about torque rheometers. Torque rheometers are based on a drive unit to which you can attach different measuring sensors like laboratory mixers and laboratory extruders. Today we will focus on the extrusion application. And if we talk about extruders, we now need to understand what kind of extruders are available out there and also for the lab. Basically, extruders are used to melt, to transport, to build up a pressure in front of a die. And for some applications, you can do changes with your material, chemical reactions inside of your extruder, or you can add and remove components, adding by secondary feeding and removing by venting, for example. If you have an extruder, you will find different designs. Most common are the so-called single screw extruders, and the industry loves these single screw extruders because they're cheap. The design is easy, so to build a single screw extruder it is pretty straightforward, but they are limited in the application. The moment it comes to compounding, to mixing, their performance not good enough. Then you have to go to at least 2 screws with the so-called twin screw extruders. If you now have 2 screws, you can now select if you want to run those screws in the same direction, the co-rotating extruders, or if you want to run those screws against each other, then you have these so-called counter-rotating extruders. The question is, which one is better? And the answer is, it depends. Co-rotating extruders are definitely the better mixers because they always give and pass the material from one screw to the other screw and then by nature already have a good mixing compounding behavior. But the counter-rotating extruders also have some significant advantages. They have a so-called chamber feeding. What happens is that the material that goes in will fill the free volume of the, let's say, right screw. And this right screw then is blocked by the left screw. When the screw is now turning, this C-shaped free volume is pressed to the end of the extruder. By this action, you have a very stiff and defined residence time. And the other thing that happens here, it works like a pump. You can generate high pressure and you also have quite good control on the shear. This is all very important if you want to process PVC dry blends. Because here we need the shear, here we need the defined residence time to avoid degradation, and we need to have the high pressure to form a homogeneous melt to get the PVC powder gelled. So we will now focus on the counter-rotators. The counter-rotating extruder we use in our lab is actually set in 2 segments. You have a gearbox at the back and the barrel connected to the gearbox, and the design is the way that you can drive away the barrel to get access to the screws. Another thing you will see with lots of these counter-rotating extruders, especially if they have to stand high forces, is that the screw is not having the same diameter along the screw, but it's actually changing. They're conical. So they're wider in the feed section and smaller at the end section. This design allows to build stronger gearboxes and have stronger bearings to stand higher forces. So, for example, with our little extruder we use today, we can then take forces up to 200 Newton meters and pressures up to 700 bar. But having conical shaped screws does not allow us to make the screws from screw segments. So we have fixed screw designs. So for the lab machine, we have 3 different designs available. Special screws, which have lower intake in the feed section to allow venting. Special intensive mixing screws, where we have breakthroughs to allow an interchange between the 2 screws to have a better mixing behavior. And the standard screws, which we are going to use today with our trial. Now, we have our extruder. Our extruder will prepare us the melt. And what we want to do today is we want to measure the flow behavior, the viscosity behavior of a PVC sample. For this, we will use our extruder as a capillary rheometer. Again, some explanations. So, first of all, what is rheology? What is viscosity? How do we measure viscosity? One thing we need to know is that viscosity itself cannot be measured. Viscosity is an inner friction of a material against its deformation. So the only thing we can measure is the effect of the viscosity. So we will apply a force on our product, on our sample, and we'll see how the sample will react on that. And from that, we can calculate this viscosity. Typical values we'll find if you talk about rheology and viscosity measurement. First, shear stress. Let's see, here we have a liquid element. We have a force that we apply on these liquid elements, and we're touching this liquid element in a certain area. And this relation of the force to the area, that's the shear stress. If we now deform this liquid element, let's see it like a bunch of cards. If we deform it, the upper card will move fastest. The lower card will stick to the bottom and will not move at all. This relation, this displacement, this is called the shear rate. And if we know this shear stress and this shear rate, we can calculate the viscosity. Now, if we look for different type of rheometers, there are different measuring principles. Very classical rheometer, rotational rheometers, they're using cones, cone plate, plate systems, or beaker system for low viscous material. And traditionally, we apply a movement, we rotate and we measure the torque that is generated by the sample. For our PVC sample, we will measure differently. We are going to use the principle of a capillary rheometer. In the classical capillary rheometer, the material is molten at a cylinder, and a piston will displace the material and press it through a flow channel with known geometry. And as a measuring value, we will measure the pressure that is generated by the sample to flow through this capillary. Some things we need to also to know about our material, and this is that the viscosity of a polymer is depending on the shear rate, on the flow speed. At low flow speed, it has a high viscosity, a higher viscosity, and it behaves like an ideal Newtonian liquid. So in the beginning, a change of shear rate does not change the viscosity, but at a certain flow speed, at a certain shear rate, the entanglements between our polymer chains are loosening, the polymer chains are aligning in flow direction, and because of that, the viscosity is dropping, so that we have this shear-thin region. This is normally the region where you also process your material in the extrusion process in your production. Theoretically, we could increase the shear rate more and more, and we would come to a second Newtonian plateau. There we have reached absolute no entanglements anymore, optimum alignment in flow direction. But normally these shear rates are so high that the material degrades before reaching that. So this is more a theoretical thing. So we are more interested in this shear-thin region. So what we were going to do during our test, we will run our extruder at defined speeds. So we will run different speed steps. And we will measure the pressure in front of such a measuring capillary, or in our case, even inside our measuring capillary. For each speed step, we will measure the output with a balance. From that, we can calculate the shear rate. And from the pressure we are measuring, we can calculate the shear stress. And then we step by step change the speed. And by doing so, we get different measuring points. And by increasing speeds, we will then see how the viscosity is dropping. And so step by step, we will come up with our viscosity curve. For the extruder, we have two different die types available, so-called slit capillary or slot capillary dies. They have a wider flow channel and have a big advantage that we can put the measuring sensors, the pressure transducers, directly into the flow channel. And there are rod capillary dies. They have a more smaller, round flow channel. Here we have the challenge that we cannot place our measuring sensor, our pressure transducer inside. So we actually measure an entrance pressure effect that needs to be corrected. Principle with both dies is the same. We measure a pressure gradient, so the pressure drop along a certain distance. From that, we can calculate the shear stress, and we measure the output. From the output, we can calculate the volume flow, and from that, the shear rate. And in the end, we come to our viscosity data. The whole measurement is based on an assumption that we have laminar, stationary, and isothermal flow. Means that we have a nicely developed flow parabola, that the material sticks to the wall of our capillary, and that our material is not compressible. Also, the flow capillary should be at least 10 times longer than the diameter. Let's have a look into our slit capillary die. As I said, the nice thing here is that we can place our pressure transducers directly inside of the flow channel, so we can measure directly the pressure drop in relation to the die lengths, and any entrance pressure effects are not affecting our measurement. But even with a slit capillary die, we have to do some corrections. The calculations we do during the measurement to come to our shear stress and our shear rate are based on the assumption that we are having Newtonian liquids, so ideal liquids. Means those liquids don't change their viscosity depending on the shear rate. But we don't have that. We've just learned we have shear thinning materials. So what the computer or the software will do is, after we did our measurement, it will calculate a polynomial that fits into our measuring points. And with this polynomial, he will calculate the inclination of our measuring point in this flow curve, and you will use it as a correction factor. So because of that, you will first see during the measurement so-called an apparent shear rate. And after the test, after doing the correction, we will come up to the absolute, to the true shear rate. So this is after we did the necessary correction. Fortunately, the software will do that for us. So, short look again on the principle of the test we are going to do. We have our extruder. Our extruder will prepare the melt. Then the extruder will press it into our measuring capillary. We will measure the pressure drop inside of the die. And to calculate the shear rate, we need to measure the output. So what we do is we will cut our sample for a defined time, and then we will place this cutted material on a balance. And with this, we can then calculate what was the mass flow, from that what was the volume flow, and from that what was the shear rate. So let's get the extrusion started. First we fill in our PVC dry blends into the hopper, and we start at low speed just to see how the material is feeding into the screws. What we see here already, material is coming out, flowing out, and we do see a nice material, hot. Here in front, we do see our slit capillary die. From the bottom, we have these 3 pressure transducers to measure the pressure drop. Actually, we only need 2 pressure transducers to measure the pressure drop. Why we use a third one? With the third one, we can check if the pressure drop is linear. And with this, we know that we have a laminar flow, and our measurement results we measure are relevant. So after now material is coming out of the extruder and everything is on steady state, we are going to run our trial. I've told the software to prepare different steps. So I told the software to start at 5 RPM of the extruder and to make 5 steps up to 35 RPM of the extruder. For each step, I will then cut the material and put it on a balance, and from that we will get the shear rate, and the software will also measure the pressure drop. And from that we will then get our viscosity curve. So let's get started. Let's simply start the measurement. Now the software is checking if the temperatures are in an acceptable range. Acceptable, I said ±1 degree. For me, it's important that the die is exactly at temperature and it looks fine, so I accept that. And now the software checking when we're having steady state and will give me a signal when to cut. So that was the first signal. I'm now waiting for the second one. I told the software that our measuring interval should be 30 seconds. So between the beeping noises should be 30 seconds. Only for the last sequence, I've reduced the measuring time down to 20, simply to not waste too much material, because the last step will be at high speed. So let's put it on a balance. About 8.1 gram. The balance is connected to the computer. So this 8.16 gram is already recorded, and if I say OK, it takes this value and automatically goes to the next speed step. Now at that speed, again, software is waiting for steady state. And we do that 5 times, because that's what I told the software to do. So 12.9, next step. And in the graph, you can already see how our viscosity curve is growing. We have 2 measuring points. The green one is the shear stress against the shear rate. The dark one is the viscosity against the shear rate. And we see how the viscosity is dropping due to the shear setting effect. Okay, and now the last speed. So extruder now at 35 RPM. You can see quite a bit of torque. We are at 160 Newton meters. We wait for steady state. Here we are. As I said, now I'm just collecting for 20 seconds because we have significantly more material coming out of the extruder. Oh, our last measuring point. Okay, measurement done, looking good. And what you may have recognized, the extruder is now back to the 5 RPM we started with, so that's also something we have programmed before. And now we want to check if what we did is reproducible. So we will simply run the same trial again. So I again start the measurement job. Our measurement seems to be reproducible. Okay, that's good. After we've done our measurements now, let's have a closer look into our results. Here at the bottom, let's enlarge that scale. Here we see our 2 measurements overlaid, and we see that the measurement is nicely reproducible. But let's also look back into our raw data. I will just look to make it more easy for one measurement. Here we can see what we've done during our trial. We ran at different speeds. Resulting to that speeds, we had different pressure inside of the die. And from that, we calculated the shear rate and shear stress. Let's have again a closer look to our viscosity results. I mentioned in the beginning that we actually need to do corrections to come from the so-called apparent values to the corrected values. And that's what I'm going to do now. I go for the calculation and do the correction for the slit capillary dye, which is only the correction according to Weissenberg-Rabinovich. And let's calculate. We see here now a third curve appearing. Here is the viscosity curve of our material after applying the correction. So now we have this function. Now another question is what I'm going to do with this data. One option is you can use this viscosity data for simulation problems. So there are software packages available on the market, MoldFlow, CAD-Mold, which allow you to simulate and calculate flow profiles for molds. For that, very often these models ask for factors of rheological models. So what that means is we have to do a regression analysis with our data. Also here, the software offers different options. So we select the corrected viscosity, and we will see if a Karo-Yasuda model will fit into our measurement. Karo-Yasuda model means these people have developed a mathematical formula that describes the natural flow behavior of polymers. The software will now calculate the factors of the formula and fit it into our measurement. With this, we have a mathematical way to express the flow behavior of my material. Now, it calculated, and let's post that. So from our measurement data, it calculated this red curve, which fits to this model. So what we have now is factors of the mathematical model, and we have the mathematical equation. So we can use that for modeling purposes. And the next step for us is we are going to clean the machine. Before I open the barrel, I remove the cooling. We've used the circulator to cool the feed section. And now I have to open the clamps at the side. And I should be able to drive away the barrel from the screws. For cleaning purposes, I can slowly rotate the screws, which makes life more easy for cleaning. So here I know just, and the nice thing with PVC, simply peels off. Okay, that's it. Screw is clean. And the next thing I would do is now cleaning the die and brushing the barrel. But this is not part of the webinar. I would now be open for questions from your side.